everybody, hiya! I've got my shoulder pads on, I am ready to teach you some physics. Light, music, rainbows and energy, which definitely includes electricity. Electricity, what is it? We've got to look at this again. We look at this every week, don't we? Everything in the world is made of atoms, little particles, balls. If you look really closely at an atom, you'll see that it's got positively charged particles in the middle called protons and negatively charged particles whizzing around the outside called electrons. And all charges really mean is that it's a bit like magnets, opposites attract. So a positive particle and a negative particle will be attracted to each other, and two negative particles, two electrons, will push away from each other. And we've seen before, it's very easy to pull electrons off atoms. So let's do that now. I know you guys love doing this. If you've got a plastic bag, get a nice sort of hand-sized bit, like that. You know what I'm going to say, rub it on your hair. This is why I've given myself a lockdown fringe. So what you're doing there, you do that, is you're pulling electrons off the atoms in your hair and you're putting them onto the plastic bag. So you're pulling negative charge off your hair and you're putting electrons, negative charge, on your plastic bag. So your bag's a bit negatively charged. So what's going to happen if I put my positively charged hair next to my negatively charged bag? Yeah, see? It's going to attract. Told you, didn't I? Opposites attract. Now, let's do something a bit different. If I get a balloon and I give that a rub on my hair, do the bag again. If I put these two things together, what's going to happen? Let's have a go. Predict people. What's going to happen? Oh, can you just see that they are pushing away from each other? That balloon is not being attracted to the plastic bag, is it? And that's because they've both got a negative charge now. So there's electrons on my plastic bag, there's electrons on my balloon, and they are pushing away from each other. So there you go. Now that was a recap, because we have covered static electricity before. If you've seen my electricity lesson, we looked at things that conduct heat and electricity. That's static electricity because the charges aren't moving. They are static. What we're going to look at today is what happens when charges move. It's like proper electricity. When charges flow, it's called a current. That's what makes our lights work. It could be protons flowing, it could be electrons flowing. Any flow of charged particles is an electric current, but realistically in like dishwashers, washing machines, clocks, everything, it's going to be electrons, because metal is a very, very good conductor of electricity because it's got loads of electrons that we call free electrons. They're just sitting in the metal and they're just waiting for an excuse to move. So let's get some electrons moving. I just found this experiment out while I was researching this. I'm so happy with this. You rub a plastic bag on your head, you get some electrons on it, and then you've got to quite quickly, but obviously gently, because this light bulb is made of thin glass, stick it on the bottom and see what happens. Now, it's best done in a dark room. I suggested that you might want to make a den or get under a duvet. If you've got an adult with you that thinks that's a good idea, you should do that now. If you haven't got an adult with you, please don't try it, because you don't want thin glass in your duvet. If you're not going to do it, you can help me, because I've built a den, right? And I was sure that I was going to show you something brilliant today, but actually when I got in my den this morning to try and test this, I don't think that the light bulb is giving off enough light for my mobile phone camera to pick it up, but we're going to try. Right, so let's go in. But only you can tell me that, because obviously I can't really tell, because I can see the real flash, so I can't tell if it's flashing on my screen. Right, did you get what you're supposed to do if you're doing this at home in your den? Rub the plastic bag on your hair, and then quite quickly, but gently so you don't break the bulb, touch it to the bottom of the bulb. Okay, so you can see the bulb, right? Here we go. This is theory of science, you see. It's not good enough to just say, oh, it doesn't work, I'm not going to do it. We need to try it, don't we? And make absolutely sure that it didn't work. I gather that you couldn't really see that. I'm going to tell you the story of Thomas Edison today, who you might have heard of. Who the story is that he's really not a very nice person, but he did have this brilliant quote He got loads of things wrong, and he said, I have not failed 1,000 times. I have successfully worked out that 1,000 things don't work, or something like that. Try that trick when it's dark. You should do it, it's cool. This is what we call a circuit diagram. If you're an electrician or an engineer, you work with electricity all the time, you don't want to have to keep drawing light bulbs when you want to tell people what you mean. So we use these cool little symbols instead. So this is a symbol of a battery, and this is a symbol for a light bulb. And this is a simple circuit that you might find inside a torch. It's just got a battery and it's linked up to a light bulb with a wire. And it's a full circuit, it's a complete circuit, so it's going to work. And what happens is, electrons in the metal wire, if you've got a battery with you, you can have a look at this yourself. You'll see that the battery has got a little positive symbol on it. It might have a negative as well. And that's because when you attach a metal wire to a battery, electrons, negatively charged particles in the wire, move away from the negative end and move towards the positive end. So the battery gives the electrons energy, and they move through, give their energy to the bulb, which lights up, and then they come back to the battery and get more energy. That is quite similar to a pizza delivery person picking up some pizzas, taking them to a house, delivering the pizzas, and then coming all the way back to the pizza shop and getting more pizzas. And it's really quite a good model, this, in a lot of ways. So if you got a break in the road, if the road broke, then the pizza delivery person wouldn't be able to get the pizzas to the house. And it's the same with your circuit. If there's a break in the wire, then the current can't flow and your bulb won't light up. But if you were to, say, build a bit of more road, or create some sort of cycle lane, then the pizzas would be able to get to the party. And it's the same if we just put a little wire around our break there, then the electrons can get through and that bulb would work. If your shop ran out of pizza, then none of your houses would be able to get pizza. What's that like? If your shop runs out of pizza, the house can't have any pizzas. What's that like on this circuit here? You might be saying it's like a battery running out of energy. So you'd be right. So in this model, the delivery people are the electrons and the pizzas are the energy. So the people pass through the shop, get some pizza, take it to the house, and then they don't have any pizzas left, so they come back to the pizza shop to get more pizza. Here it's the same thing. So the people are the electrons, the pizza is the energy, okay? And the house is the bulb, and the battery is the shop. What if it's a really big party happening here? Okay, how would that change this model? If that was a really, really big party, you'd need loads of pizza, wouldn't you? And if you have a look on your battery, you will see a number and with a V next to it. So I'll show you this one because we're going to look at this a bit later on. So that's 9V. V stands for volts, and volts is, in this model, volts is essentially how many pizzas per driver. Voltage just means how much energy each electron has. It's energy per charge. So in this model, your voltage is pizza per delivery driver. So if this driver's got like 3 pizzas, then this would be a 3-volt battery. If it was a really big party, then it would need more energy. So if you've got a really big bulb, you'd need a battery with a bigger voltage. You might need a 9-volt battery so the party could have 9 pizzas. If you put in a 3-volt battery, but you've got a 9-volt bulb, then what happens? Well, if you only delivered 3 pizzas to a massive party, what would happen? It'd be quite a rubbish party. And it's the same over here. If you've got a lower voltage battery than your bulb needs, then the bulb, you'll find, will be very dim. So there you go. If you're ever confused about electricity, think about pizza. It's nearly time for story time. One thing I want to show you, because we're going to think about the fence in Jurassic Park at the end of the lesson. Have a think for me. Would this, I mean, it's GCSE level question, so, you know, don't worry if you haven't got a clue. But would this bulb light up in this circuit? Would that bulb light up? The answer is No, because these electrons have to have a reason to move, and they're moving because they're getting away from the negative end of the battery and towards the positive end. But if they go this way, there's not any sort of difference across this wire, so they're not going to travel that way. Okay, that's important for later. Another reason this is a good model is what if there were two houses? Oh, say two houses exactly the same size. What would probably happen is that the pizza delivery people would want to drop an equal amount of pizzas at each house. I'll have to pretend that they only had two pizzas. So if it's a 2-volt battery and you put in 2 bulbs, then the voltage is shared out across the bulbs. It's exactly the same with actual bulbs. These bulbs would be dimmer than if you just had one bulb, because the energy has got to get shared. How does the electron at this point know that this bulb is here? I'm getting my bulbs and my parties confused, but you know what I mean. So electron comes along. Why on earth doesn't an electron just dump 2 pizzas there and then that bulb doesn't light up? It's mad, isn't it? Electricity, it's just brilliant. Okay, on that note, I'm going to quickly tell you that there are 2 different types of electricity: DC and AC. DC means direct current, and that's what you get in battery operated stuff and loads of other stuff actually, and that just means that the current travels just in one direction like that. AC, alternating current, is where the electrons kind of vibrate backwards and forwards. You don't really need to know about AC and DC, except I'm about to tell you a story about 2 men who had a massive battle over the difference between AC and DC. Right, yeah, it's story time, let's go, I'm excited about this one. Have you ever heard of Thomas Edison? And if you have heard of him, can you tell me what he did? Some of you might be saying that Thomas Edison invented the light bulb. You're absolutely right. A lot of people have heard of Thomas Edison. He's very famous. He's in that song, isn't he? They all laughed at Christopher Columbus when he said the earth was round. They all laughed when Edison recorded sound. That song's talking about Thomas Edison. He did record sound. Yes, he's famous for being a brilliant inventor. We're going to see about that. Have you ever heard of Nikola Tesla? Despite the fact that the Tesla company and the Tesla car are named after him, a lot of people still haven't heard of Nikola Tesla. This is the story of Nikola Tesla and Thomas Edison. So Nikola Tesla was born in Croatia in the 1850s. He was a fascinating child. He read loads of books. He could memorise books. He learned 8 different languages. Very, very good at school. Went to university to do electrical engineering and got into quite a lot of fights with his lecturer because his lecturer kept trying to teach him about motors that used direct current. And Tesla kept thinking, I don't know about that. I don't think that motors should really run on direct current. And do you know what? He became so obsessed with the idea of motors that run on AC, alternating current, that he actually couldn't concentrate at school and ended up dropping out of university. Which isn't dissimilar to Edison. Fantastic reader, but struggled at school. He was called a hyperactive child. He was called a difficult child. He ended up spending 12 weeks at school before his mum pulled him out of school and decided to home educate him. Now, he started working for a railway company selling newspapers. Now, you're Edison, you're working for a railway line, they're getting telegrams all the time of the absolute latest news, you're selling newspapers, you're making a bit of money, what do? He started up his own newspaper. He used all the news to build his own newspaper, and everybody loved it, and it ended up making him loads of money. So I can't criticise Edison for that, and I don't think anybody would. He was a fantastic businessman. This is the sort of thing he does his whole life. He sees opportunities and he grabs them. Now, unfortunately, for the people who get in the way, he's not always nice about it, but there you go. He worked incredibly hard, worked a lot of night shifts, came from a poor family, but in the end was doing very, very well for himself. At the point when sailed across to New York. Eventually, actually after reciting poetry in a park, had solved his AC motor problem. He developed a motor that could run on alternating current. He was really happy with it. So off he goes to New York. He's got no money, but he has got a letter in his pocket from his old boss. And that letter is addressed to Thomas Edison. And the letter says, "My dear Edison, I know of two brilliant men in this world. You are one of them, and this is the other one." So Edison says, "Oh, hello, welcome. Great, sounds like you could be useful." Edison by now is running this enormous factory. He's got a team of scientists and designers working for him. A lot of these people sort of probably designed the stuff and invent the things that he is credited with designing. But he's having a real problem with his DC motors. And he says to Tesla, "Look, please, if you can solve the problem of my DC motors, I will give you $50,000. We're talking 200 years ago. Imagine how much $50,000 was. So Tesla goes away, and it's Nikola Tesla. Einstein was once asked, "What's it like being the smartest man alive?" And he said, "I don't know. You'd have to ask Nikola Tesla." Tesla comes back, and he solved Edison's problem. He solved the problem of the DC motors. So what does Edison do? He says, oh, Tesla, once you've been in this country a bit longer, you'll understand the American sense of humour. And he doesn't pay him. So Tesla quits and actually ends up getting a job down the road. There's a lot of towns in America that don't have electricity. If we can work out how to get electricity from power stations to these towns, we'll make an awful lot of money. Tesla starts working on how to solve that problem using AC, alternating current. This is in direct competition to Edison, just across the road, who is trying to solve the same problem using direct current. Do you get that? That's Tesla, who's climbed a ladder and is angrily looking through the window. Yeah, it becomes sort of quite clear to everyone quite early on that Tesla has had the right idea. Edison, he can't handle it. He becomes furious and he starts doing really weird things to try and persuade the world that DC current is better. One of the things he does is give an electric shock to an elephant using AC to show everyone, look, Tesla's current is so dangerous that it can give an electric shock to an elephant, so you definitely shouldn't use it. He does other things, like he forces cats to box. It's all a bit weird. Back in his office, Tesla is doing really well. He's what we call patented his design for an AC motor, and that means that anyone who uses it has to give him some money. Now, if someone does agree to give him some money every time they sell an AC motor, he gets what's called a royalty. Unfortunately, this person, who's called Westinghouse, gets into financial difficulty, and do you know what Tesla ends up doing? He tears up the agreement that he had with Westinghouse. He was giving up millions of pounds, but he was also giving up billions of pounds in the future, okay? He's got AC motors. Everyone who uses an AC motor has to give him money. He was going to be one of the richest people on Earth. Not one of the richest people in America, one of the richest people on Earth. And because the guy is getting into monetary troubles and he thinks the guy's quite nice, he's just said, oh, well, no, all right then, don't worry about it. He's actually, by this point, he's dreaming of something else. He's had an incredible idea for wireless technology, and he's thinking about putting it into an enormous, beautiful tower where people can work. And his description of how this wireless technology works, it's uncanny. A business person in New York could immediately send their ideas to a person in London and have them written down straight away, and we can all have devices that are the size of watches, and we can listen to music on them, we can do all this stuff. It's an incredible prediction of how we live life today. He goes to someone with loads of money called JP Morgan, and JP Morgan says, okay, I'll give you the money to build this fantastic tower. So they start building it. It soon becomes clear they're going to need more money. But unfortunately for Tesla, by now, everyone is excited about a different person, someone called Marconi, because Marconi is developing radios, and he's just sent the first signal using radio waves. So instead of supporting Tesla, everyone's giving their money to Marconi. What does Tesla say about Marconi? He says, he is a good fellow. Let him continue. He is using 17 of my patents. And that is absolutely true. Marconi hadn't asked Tesla's permission to use all his ideas. And actually the court did decide that He had used Tesla's ideas unlawfully. Unfortunately, that was after Tesla died. So Tesla didn't get famous and didn't get any money for helping to invent the radio. To make matters worse, his beautiful tower, because it's run out of money, it just becomes like a hollow shell of a building and eventually is knocked down. And Tesla says, very sadly, it is not a dream. It is a simple feat of scientific engineering, only expensive, blind, faint-hearted, doubting world. And unfortunately, after that happened, Tesla's mental health really starts to suffer. He lives his final days out on the 33rd floor of a hotel. Actually, his bed and board were paid for by Westinghouse. You remember the person who he destroyed the contract so that Westinghouse wouldn't owe him millions of pounds. Don't laugh. He ends up saying in an interview that he's in love with a pigeon. I said don't laugh. That's how bad his mental health is. And yet, sadly, actually dies in debt, despite all his fantastic inventions. I mean, he was the first person to record radio waves from space. He predicted correctly something called the resident frequency of Earth. It would take 50 years before we'd invented machines that could prove that what he'd just come up with in his head was correct. That's Tesla. Edison lived a very long life and apparently was very happy. July the 10th, as I speak, that's 3 days' time, is Tesla's birthday. Maybe we can all help to remember him, and his life won't have been quite as sad as he maybe thought it was. I'm going to tell you a few shocking facts about electricity based on the questions that I asked you before we end the lesson. Could an unplugged microwave give you an electric shock? Well, yes, it could. Microwaves and washing machines as well. They need an extra surge of current occasionally to get working. Even more current than comes out of your plug sockets. So what they do is they've got something inside them called a capacitor. And a capacitor is just two sheets of metal that has electrons building up and up and up and up and up on one side. And then at the right time, the capacitor lets all these electrons flow onto the opposite plate, and that causes a big surge of current which gets the microwave working. So you could find a microwave that had been in your garage for a couple of weeks and be unplugged and think, oh, yeah, brilliant, can't get a shock from this, I'll have a go at fixing it. If you accidentally get your hand, you wouldn't even need to touch them, but if you get your hand close enough that the electrons jump to your hand and flow down to Earth, you would get a tremendous electric shock. The next question, very important one, is the fence in Jurassic Park realistic? So a lot of you won't have seen Jurassic Park yet. You should wait until you're 11 or 12. Don't waste your first Jurassic Park moment. But it's my favourite ever film. They make a theme park with real dinosaurs. Stuff goes wrong. And in one of the scenes, little Timmy is clinging to an electric fence. He's standing on a bit of the electric fence and he's holding his hands on the electric fence. And then a current flows through the electric fence. It's 10,000 volts. And Timmy gets a massive electric shock, flies off. And Dr. Alan Grant, dinosaur expert, has to bring him back to life. Would that have happened? The answer is, Callum says no. Well done, Callum. Yeah, you're quite right. For the same reason that you see birds sitting on electricity cables and they're not getting an electric shock. Electrons, remember I said, they need a reason to flow. Earth is so massive that is pretty much always neutral. It can just take loads of negative charge and still be neutral. So electrons are very happy to flow through you to get to the ground. So that's why animals standing on the ground, like the dinosaurs on the ground, when they touch the electric fence, they'd get a current flowing through them and into the ground. They would get an electric shock. But Timmy, the electrons wouldn't have any reason to flow through him. If his foot brushed against a fern or something, then it might travel through him and through the fern to the ground. But in general, sadly, it turns out Jurassic Park, not a very realistic film. And the last thing I'll tell you, before I invite some of you to leave, is electric eels can give you a shock of 40 milliamps. Now, a shock of 20 milliamps can kill you. Would the shock of an electric eel kill a human? People are saying no. No, you're absolutely right. Why not? It's because it's very, very quick. So the reason electricity is dangerous is for a few reasons. Electricity gives you a shock because of the amount of current that flows, but also the amount of time that it flows through your body. So like current is measured in amps. So 1 amp travelling through you for 2 seconds would be the same as 2 amps travelling through you for 1 second. So an electric eel, although it's giving out a lot of current, if it just gives you a tap, you would feel a lot of pain, but you wouldn't die. We'll talk about milliamps. That's really, really, really small amount of current. 10 milliamps is enough that you'd feel it and you'd be pretty tingly. 20 milliamps, it doesn't damage your heart, but if you get 20 milliamps running through your body, what happens is your muscles spasm, so you can't let go. And that's why that's really dangerous, because you remember what I said about the time that current is travelling through your body makes a big difference to how dangerous the shock is. So if you're only getting 20 milliamps, but you're holding on to the wire that's giving you the shock and you can't let go, you're going to get a really bad electric shock. It's about 100 milliamps, which causes your heart to start kind of quivering. Like obviously your heart's a muscle which beats regularly. Once it gets 100 milliamps, it starts like beating in a kind of really weird twitchy way. It's called fibrillation, and that is what's really dangerous and would kill a human. In fact, I read in a book some advice to electricians that wherever possible they should work with one hand, because if you get an electric shock and you're only using one hand, then the current will flow from your hand through your foot and into the ground, which would be really bad. But if you're using 2 hands, anyone think about why that's worse? You've created a circuit where the current is going to flow from one of your hands across your heart and out of the other hand, and it's the electricity crossing your heart which is really dangerous. Weirdly, and this seems to be true from what I've read, up to 200 milliamps your heart actually clamps and stops completely, and you're actually more likely to survive that. A higher electric shock that clamps your heart, when you've stopped getting the shock, your heart might start beating again. We actually do that with machines called defibrillators. So it's kind of like turning your heart on and off again. If your heart was doing that weird quivery thing, if you get a defibrillator that clamps your heart shut, then when you take the defibrillator off, you might find that your heart starts beating again. And something I have to tell you all about that is that you see loads of defibrillators out in public now. And that's because we did the science, and it turns out you've got to defibrillate someone really fast to save them. So if you see someone with a heart palpitation, someone struggling with their heart in the street, it's much better for you as a total amateur who doesn't know what they're doing to grab a defibrillator and have a go yourself than it is for you to think, oh no, I'll leave it to the professionals. I want to tell you a little story which all electricians are told now about a person who killed themselves. The only person we know of so far who's managed to kill themselves with one of these, a 9-volt battery. Any ideas how he did it? He'd been on an electrical safety course in the US Navy. He'd learned about something called internal resistance, and he thought he'd find out how resistant the inside of his body was. So he got something that measures resistance, and the ends of the little sensors, he spiked his fingers onto them, except that the little machine was running using a 9-volt battery, and although 9 volts isn't very much, your body has a really, really low resistance. Like, you're basically just a sack of salt water, and electricity travels through salt water really easily. So the current just went straight through his body, and he died. Yeah, he won a Darwin Award. Finally, someone called Claude Francois was the French version of Justin Bieber. Massive pop star, having a bath one night, looked up, saw that his light in his bathroom was just a little bit wonky, decided to fix it, stood up in the bath, reached out, and died from an electric shock, because water is a fantastic conductor of electricity, and the current just flowed straight through him. I will end the lesson. Thank you so much for joining me, as usual. If you could follow me on Facebook and subscribe to me on YouTube, that'd be brilliant. 2 more people supported me on Patreon just this morning. Thank you so much. It gives me such like a buzzy little feeling when you do that. Bye everybody, and I'll see you next week. Winnie89, hello, you've been coming for a while, haven't you? There's a Doctor Who episode about Edison and Tesla. Oh, well, I need to get on that, don't I? Yeah, Evan and Finley, go make your den. Good to see you. Whoa, Ruben, you came in on the volcano lesson and you're still here. That is impressive. I was so nervous at a volcano lesson. There were like 2,000 people there. Do you remember I kicked over a bowl? Oh, whoa, I am inspiring people to watch Jurassic Park. That's all I'm here for, guys. Len Sheemet, you're feeling sad about Tesla? Yeah, you should look up some of the facts that I gave you today. See you later, everybody. Thank you so much for all your support. I really enjoy these sessions. Bye.